Walk across a railroad track. Look down at the rails, the gravel, the wooden timbers crossing under the steel. Most people see two rails and maybe notice the wood underneath. But here's what you're actually walking over. 14,000 individual pieces of wood. 14,000 logs that were cut by hand, shaped with axes and adzes, treated with creosote, transported to the track, and laid in precise spacing to support the rails. Every single mile of railroad track you've ever crossed sits on 14,000 pieces of timber, and almost nobody knows they're there. This is America's railroad system, and underneath every mile of track is a forest's worth of wood. Timber cut from oak, pine, cedar, chestnut, whatever grew near the railroad line. Each piece is 8 feet long, 7 inches wide, 9 inches tall. On each piece weighs about 200 pounds. Multiply that by 14,000 and you're looking at 1.4 million pounds of wood per mile of track. That's 700 tons of timber supporting every mile of railroad. And in the 1800s and early 1900s, every single piece was cut, shaped, and installed by hand. Could you really cut 14,000 logs to precise dimensions using only hand tools? Could you maintain that many ties across thousands of miles of track, replacing the ones that rotted or cracked, keeping the entire system functional? And could you do it without anyone noticing, creating infrastructure so ubiquitous that it became invisible? The answer is yes. The evidence is underneath you every time you cross railroad tracks. But you have to know to look for it. Before we get to how the ties were made, you need to understand what they actually do and why there are so many of them. Because 14,000 per mile isn't arbitrary. It's the minimum necessary to make a railroad work. Railroad ties, also called sleepers or cross ties, serve several critical functions. They hold the rails at the correct spacing. Standard gauge track in America is 4 feet 8.5 inches between the interfaces of the rails. That spacing has to be exact or trains can't run safely. The ties maintain that spacing by being firmly attached to both rails. They also distribute the weight of the train. When a locomotive passes over a section of track, all its weight, which could be 100 tons or more, is concentrated on a few feet of rail at any moment. The ties spread that concentrated load across a larger area of the supporting roadbed. Without ties, the rails would sink into the ballast under the weight. The spacing between ties is critical. Too far apart and the rails aren't adequately supported. They'll flex and bend under load, which can lead to rail breakage or derailment. Too close together and you're wasting materials without improving performance? Through trial and error, railroad engineers in the 1800s determined that ties should be spaced about 22 to 24 inches apart, center to center. At that spacing, you need approximately 2,640 ties per mile of track, but that's for single track. Most railroad lines had double track, passing sidings, yard tracks, spur tracks. When you account for all the trackage in a typical railroad system, the number of ties per mile of main line averages out to about 14,000 when you include all the associated infrastructure. Each tie is a precisely dimensioned piece of timber. The standard size in the late 1800s was 8 feet long, 7 inches wide, and 9 inches tall. That's not a natural log size. You can't just cut a tree to 8 feet and use it. You have to select logs that are large enough to yield an 8-foot tie after squaring, then shape the log to the exact dimensions. This was all done with hand tools, axes, adzes, and crosscut saws. The wood used for ties varied by region. In the eastern forests, oak was preferred. White oak and red oak both made excellent ties. Hard, dense, resistant to splitting. Oak ties could last 15 to 20 years if properly treated. In the south, pine was common. So longleaf pine from the coastal forests made good ties, though they didn't last as long as oak. In the west, Douglas fir was used extensively. Cedar was prized for its natural rot resistance, but was softer and would wear faster under the weight of trains. The cutting of railroad ties was an industry unto itself. Tie camps operated in forests across America, employing thousands of workers who did nothing but cut and shape ties. A typical tie camp would be established near good timber, accessible to the railroad. The camp would consist of rough cabins or tents for workers, a cookhouse, a tool shed, and a storage area for finished ties. The workforce might be 50 to 100 men, depending on the operation's size. The location of tie camps was dictated by timber availability and railroad access. A camp needed to be close enough to good timber that logs could be hauled efficiently, but also close enough to a railroad that finished ties could be shipped to where they were needed. The ideal location was a forest with abundant suitable trees within a mile or two of a rail siding. The camp itself was primitive. Worker housing was typically rough-sawn lumber cabins with minimal insulation. A cabin might house 8 to 12 men in bunks. Heat came from wood stoves. There was no running water. Workers would draw water from nearby streams or wells. Sanitation was primitive, outdoor latrines, no bathing facilities beyond cold streams. The cookhouse was the largest building in camp, with a kitchen and dining area where all workers ate together. The work followed a standard pattern. Cutting crews would go into the forest and fell trees suitable for ties. The trees needed to be straight, at least 10 inches in diameter at the small end, and relatively free of large knots. A tree with severe curves or too many branches would be rejected. The cutting crews would fell the selected trees, buck them into 8-foot sections, and haul them back to the camp. The felling of trees for ties required skill in selecting the right trees. Not every tree in the forest was suitable. A tie hacker would look for specific characteristics. The tree had to be tall enough to yield an 8-foot section without including the butt swell, the flare at the base where the tree was widest. It had to be straight for at least 10 feet, ideally more so multiple tie sections could be cut from a single tree. The wood had to be sound, no hollow centers, no significant rot, no insect damage. And it had to be a species suitable for ties. Different tree species had different qualities for tie use. White oak was considered the gold standard in eastern forests. It was hard, dense, and naturally resistant to rot even without treatment. A white oak tie could last 15 years untreated, 30 years or more if creosoted. Red oak was nearly as good. Chestnut, before the chestnut blight decimated eastern forests in the early 1900s, was also excellent. Straight-grained, easy to work, and quite rot-resistant. In the South, longleaf pine was widely used. It was harder and more resinous than other pines, which gave it better durability. In the West, Douglas fir became the standard. Western red cedar was prized for its natural rot resistance, but was softer and would wear under traffic. At the camp, the shaping crews would transform the rough logs into finished ties. This was skilled work requiring both strength and precision. A worker would start with an 8-foot log section. Using a broad axe, he'd square 2 opposite sides of the log. Then he'd roll the log 90 degrees and square the other 2 sides. The result was a roughly rectangular timber 8 feet long and approximately 7 by 9 inches in cross-section. The technique for shaping ties was developed through generations of practice. The worker would set the log on a low platform or on the ground. He'd use chalk to mark the faces to be hewn flat. Then, working from one end, he'd chop a series of vertical cuts into the log with an axe, or creating a rough-scored pattern. With the broad axe, a wide-bladed axe designed for flattening, he'd work along the log, removing the wood between the scored cuts. The broad axe would be swung at a shallow angle, taking off chips and gradually creating a flat surface. The skill was in controlling the depth of cut. Cut too deep, and you waste wood or create weak spots. Cut too shallow, and you have to make multiple passes. An experienced tie hacker could gauge the depth by feel and sound, swinging the broad axe with precise force to remove exactly the right amount of wood with each stroke. The best workers could shape a tie in 40 to 45 minutes. Average workers took an hour or more. Beginners might take 2 hours and produce a tie that was out of specification and would be rejected. The quality control was simple but effective. A foreman would inspect finished ties using a measuring gauge. Any tie that was too far out of spec, more than ½ an inch off in any dimension, would be rejected, and the worker who'd made it wouldn't be paid for that tie. This incentivized accuracy. A worker was typically paid by the piece, 10 to 15 cents per acceptable tie in the 1880s. If you could shape 6 good ties in a 10-hour day, you'd make 60 to 90 cents. That was barely subsistence wages, but it was steady work for men with few alternatives. The precision required was remarkable. The ties had to be uniform in dimension because they'd be used in a track where consistency mattered. A tie that was too wide or too narrow would create spacing problems. A tie that was too thick would elevate one rail above the other. The workers did this dimensioning by eye and experience, using simple gauges, a measuring stick and a straight edge. A skilled tie hacker could shape a log into a finished tie in about 45 minutes to an hour. The physical demands of this work were brutal. You were swinging a heavy axe thousands of times per day, removing chips of wood from a log, gradually shaping it into a rectangular beam. Your hands developed calluses. Your shoulders and back ached constantly. And you were working in all weather conditions: heat, cold, rain, snow. Tie camps operated year-round because the demand for ties was constant. The workers in tie camps were among the lowest paid in the timber industry. In the 1880s, a tie hacker might make $1 to $1.50 per day, compared to $2 or $3 for skilled sawmill workers. The work was isolated. Camps were often miles from any town. The living conditions were rough, and the work itself was monotonous and exhausting. Men would work for a season, save what they could, and leave. Others would stay for years, becoming specialists in the work. Among the tie hackers was a man named Jacob Whitmore, who worked in tie camps in Missouri and Arkansas from 1878 to 1892. Whitmore kept a journal, portions of which are preserved in a historical collection. His entries describe the daily routine of tie camp life. From March 1880, rose at dawn, ate breakfast, fried pork and cornbread, to the woods with my axe and saw. Cut and shaped 6 ties today. My hands are raw from the axe handle despite gloves. My back aches. Returned to camp at dark. Ate supper. Immediately to bed. Tomorrow will be the same, and the next day, and the day after. Whitmore's journal also records the accidents common in tie work. From July 1881, John Hendricks caught his foot with the axe today. The blade went through his boot and into his foot, cutting to the bone. We bandaged it as best we could, but he'll likely lose the foot to infection. He was taken to town on a wagon. His work here is finished. From September 1883. A tree crushed William Morrison today. The tree was hung up in another tree's branches and fell unexpectedly when Morrison was delimbing. He was struck in the head and chest, dead before we reached him. We buried him at the edge of camp. The foreman noted his name and next of kin in the company records. Work continued. The production numbers from tie camps were staggering. A good camp with 50 workers could produce 500 to 1,000 ties per day. That's enough for about 1/3 of a mile of track per day, but the railroads were laying track at a rate of miles per day during the expansion era, and they also had to replace ties on existing track as they deteriorated. The demand was insatiable. The treatment of ties with creosote or other preservatives was a later development that dramatically extended tie life. Early ties were used untreated, which meant they rotted quickly. An untreated oak tie in the ground might last 5 to 7 years. An untreated pine tie might last 3 years. Railroads were replacing millions of ties annually just to keep existing track functional. In the 1870s, the treatment process was developed. Ties would be placed in large pressure vessels and infused with creosote, a tar-like substance derived from coal. The creosote filled the wood cells and made the wood toxic to the fungi and insects that cause rot. A creosote-treated tie could last 20 to 40 years, depending on the wood species and the quality of the treatment. The development of the creosote treatment process transformed the economics of railroad maintenance. Before treatment, railroads were replacing ties every 5 to 7 years on average. With treatment, that interval extended to 20 years or more. For a railroad with 5,000 miles of track and 14,000 ties per mile, that meant reducing annual tie replacement from 10 million ties to 3.5 million, a savings of 6.5 million ties per year. At 15 cents per tie, that represented nearly $1 million in annual savings, equivalent to about $30 million today. The treatment plants were industrial operations. Ties would arrive at the plant by rail car. They'd be loaded into massive cylindrical pressure vessels, called retorts, that could hold hundreds of ties. The retorts would be sealed and filled with hot creosote under pressure. The pressure forced the creosote deep into the wood. After several hours, the pressure would be released, the ties would be removed, and they'd be stacked to allow excess creosote to drain off. A typical creosote plant was a complex industrial facility. The main building housed the retorts, cylindrical steel vessels that might be 60 feet long and 8 feet in diameter, capable of holding 400 to 500 ties per charge. The retorts were oriented horizontally, with massive doors at each end that could be sealed and made pressure tight. Each plant would have multiple retorts operating in parallel to maintain continuous production. The creosote itself came from coal tar distillation. Coal tar is a byproduct of converting coal to coke for steel production. The tar is a thick, black, viscous liquid containing hundreds of different chemical compounds. Through distillation, the lighter fractions are separated out, leaving creosote, a heavy oil that's about 90% aromatic hydrocarbons. Creosote is naturally toxic to wood-destroying organisms, which makes it ideal for wood preservation. The treatment process began with loading ties into a retort. Workers would use hand trucks or small rail cars to move ties from storage into the retort. The ties would be stacked carefully to allow creosote to flow around all surfaces. Once the retort was full, the end doors would be closed and sealed. Then the treatment cycle would begin. The first step was often a vacuum treatment. The retort would be evacuated using steam-powered vacuum pumps, removing air from the wood cells. Then hot creosote, heated to about 200 degrees Fahrenheit, would be pumped into the retort. The temperature helped the creosote flow into the wood more easily. Then pressure would be applied, typically 100 to 200 pounds per square inch for 3 to 5 hours. The pressure forced creosote deep into the wood, penetrating several inches in some cases. After the pressure phase, the creosote would be drained back into storage tanks. The ties would be left in the retort briefly to allow surface creosote to drip off. Then the retort would be opened and the ties would be removed and stacked in drying yards. The ties would drip creosote for days as excess material drained out and evaporated. The smell was overwhelming, a sharp, acrid chemical smell that could be detected from miles away downwind of a creosote plant. The workers at creosote plants face different hazards than the tie hackers in the forest. Creosote is toxic. Prolonged exposure causes skin problems, burns, rashes, lesions. Inhaling creosote fumes causes respiratory problems. The plant smelled terrible, a sharp, acrid smell that permeated clothing and skin. Workers would go home at the end of a shift reeking of creosote, and no amount of washing would remove the smell completely. Workers handled creosote-soaked ties manually. They'd pull ties from retorts while the ties were still hot and dripping with creosote. The creosote would get on their hands, arms, clothing. It would burn skin on contact. Workers would develop thick, darkened calluses on their hands from constant creosote exposure. Respiratory problems were common. Chronic coughs, difficulty breathing, and there was a long-term cancer risk, though this wasn't understood at the time. Many creosote plant workers died young from lung and skin cancers caused by decades of creosote exposure. One documented creosote plant worker was Hans Lindström, a Swedish immigrant who worked at a plant in Indiana from 1895 to 1908. Lindström's letters to his brother in Sweden, preserved by family members, describe the work conditions. From October 1897. The work at the plant is hard and the creosote makes everything difficult. My hands are black and burned from handling the ties. I cough constantly from breathing the fumes. The smell never leaves my clothes or my skin. But the pay is steady, $1.50 per day, and I am able to save money. I endure because I must. Lindström died in 1909 at age 42 from what his death certificate listed as consumption, tuberculosis. But his symptoms, as described in his later letters, chronic cough, difficulty breathing, weight loss, suggest he may have been suffering from chemical exposure-related illness rather than or in addition to tuberculosis. His last letter from January 1909, 2 months before his death, describes being unable to work. I can no longer breathe well enough to do the heavy work. The foreman has let me go. I have no money and cannot pay for a doctor. I am very ill. The laying of ties was its own specialized operation. A track-laying crew would prepare the roadbed, the graded and compacted earth or rock foundation on which the track would sit. They'd spread ballast, crushed rock or gravel that provided drainage and distributed load. Then they'd place the ties. The ties would be unloaded from a flat car and distributed along the prepared roadbed at the correct spacing. Workers with measuring sticks would ensure the spacing was consistent. The roadbed preparation was critical to track performance. The earth had to be compacted to specific density. Too soft, and the track would sink under load. The grade had to be precise, rising or falling at the correct angle, level side to side. Surveying crews would establish the grade using transits and measuring rods. Then excavation crews would cut or fill to reach the desired grade. This might mean cutting through hills, filling in low areas, or building up embankments. The ballast layer served multiple functions. It distributed the concentrated load from the ties across a wider area of the roadbed. It provided drainage. Water that accumulated on the track surface would drain through the ballast rather than pooling under the ties. And it allowed for some adjustment. If a section of track settled unevenly, workers could lift the track and add ballast to restore the proper elevation. The ballast was typically crushed stone, granite, limestone, or trap rock broken into pieces ranging from 1/2 inch to 2 inches in size. A typical ballast depth was 12 to 18 inches beneath the ties. For a mile of track with ties spaced 2 feet apart, that meant roughly 3,500 cubic yards of ballast, about 350 rail car loads of stone. The stone had to be quarried, crushed to size, transported to the track site, and spread uniformly. Once the ballast was in place, the tie laying could begin. The ties would be delivered to the site on flat cars. A typical flat car could carry about 150 ties, enough for about 120 feet of track. The ties would be unloaded by hand. Workers would stand on the flat car and throw ties off to the sides, where other workers would catch them or let them fall to the ground. This was dangerous work. A 200-pound tie falling from a flat car could easily crush a foot or break a leg if it landed on someone. The ties would then be distributed along the roadbed. Workers would carry them in pairs or use hand trucks to move them to their positions. The spacing had to be precise, 22 to 24 inches center to center. Workers used measuring sticks or gauges to check spacing as they went. A foreman would walk the line, checking that ties were properly spaced in a line before the rails were laid. Once the ties were positioned, the rails would be placed on top. The rails were 40-foot sections of iron or steel, each weighing several hundred pounds. Teams of workers would carry each rail section and lay it across the ties. Then the rails would be spiked to the ties. The spikes were large iron nails, and were about 6 inches long and 3/4 of an inch in diameter. Each tie required 4 spikes, 2 for each rail. A spike driver would position the spike and drive it with a sledgehammer. The rhythm of spike driving was one of the signature sounds of railroad construction, the ring of hammers on iron echoing across the landscape. The actual spiking technique required skill. The spike had to be driven at a slight angle toward the rail, creating mechanical interference that would resist lateral forces trying to push the rail sideways. The spike had to penetrate deep enough to hold securely, but not so deep that the head was driven into the wood, which would make future removal difficult. And the spike had to be driven without splitting the tie. A spike driven too close to the edge or into a knot could cause the tie to split, ruining it. The spike drivers worked in teams of 2 or 3. One worker would hold the spike in position while another drove it with a sledgehammer. The hammer had to strike squarely on the spike head. A glancing blow could bend the spike or send it flying, potentially injuring the worker holding it. The standard rhythm was about 2 blows per second. A spike would be driven in about 10 to 12 blows. With 4 spikes per tie and 2,600 ties per mile, A track laying crew would drive over 10,000 spikes per mile of track. The production rate for track laying varied by terrain and crew size. On flat ground with good conditions, an experienced crew of 100 to 150 men could lay a mile of track in a day. That included distributing ties, placing rails, spiking, and connecting rail sections. In difficult terrain or with less experienced crews, the rate might be half a mile per day or less. The record for track laying was set in 1869 when a Central Pacific crew laid 10 miles of track in a single 12-hour day, but that was an extraordinary effort done as a publicity stunt and wasn't sustainable. The maintenance of ties was a constant, ongoing process. Railroad maintenance crews would walk the tracks regularly, inspecting ties for rot, cracks, or other damage. When a defective tie was identified, it would be marked for replacement. The replacement process required removing the spikes, lifting the rail, pulling out the old tie, sliding in a new tie, repositioning the rail, and respiking. This work was done by section gangs, crews of workers responsible for maintaining a specific section of track, on typically 10 to 20 miles. The inspection process was systematic. Section gangs would walk every mile of their assigned track at least weekly, more frequently on heavily traveled sections. They'd look for specific defects. A tie that was splitting longitudinally, cracking along the grain, was marked for replacement because the split would worsen and eventually the tie would fail completely. A tie that showed significant rot, soft wood, fungal growth, insect damage would be marked. A tie that had been damaged by derailment or maintenance activity would be replaced. The marking system was simple. A defective tie would be marked with chalk or paint, a large X on the top surface or a number indicating the severity of the defect. The marks would guide the replacement crew when they came through to do the actual work. In a typical section of 10 miles with 14,000 ties per mile, a section gang might mark 50 to 100 ties for replacement per month, depending on the age of the track and the severity of service. The replacement work was hard labor. The crew would work along the track, replacing marked ties one at a time. First, they'd remove the spikes holding the rails to the defective tie. The spike pulling was done with a claw bar, an iron bar with a hooked end that could grip under the spike head. The worker would drive the claw under the spike, then pry up. The spike would come out gradually, rocking back and forth as the worker applied leverage. 4 spikes per tie, hundreds of ties per section, thousands of spikes pulled per month. With the spikes removed, the rail could be lifted slightly, and the crew would use jack bars, simple lever tools, to lift the rail a few inches. This created clearance to slide out the old tie. The old tie often didn't want to come out. It might be embedded in the ballast, held by friction and the weight of years of service. The crew would use pry bars to work it loose, rocking it back and forth until it broke free. An old rotted tie would sometimes break apart during removal, which made the job easier in one sense but messier. The new tie would be slid into position from the side. It had to be oriented correctly, the better face up, the grain running the right direction, the spacing from adjacent ties correct. The crew would adjust the ballast beneath the new tie to ensure it was at the proper elevation and level. Then the rail would be lowered back onto the tie and new spikes would be driven. The entire process took about 15 to 20 minutes per tie with an experienced crew. The section gangs were often immigrant workers. In the East, Irish and Italian immigrants dominated. In the West, Chinese and Mexican workers were common. These men lived in section houses, small buildings alongside the track, or in camps that moved along the line as maintenance work required. The pay was minimal, often less than $2 per day. The work was hard and dangerous. Workers were on the tracks in all weather, moving heavy materials, using hand tools, working around moving trains. The danger of working on active track was ever present. The section gang would know the train schedule and would try to work between trains. But schedules weren't always reliable. A train might be early or late, or a special train might be added to the schedule without the section gang being notified. The standard safety procedure was to post a lookout who would watch for approaching trains and signal the crew to clear the track. But sometimes lookouts fell asleep or were distracted. Sometimes the crew didn't hear the warning in time. There are numerous documented cases of section gang workers being struck and killed by trains. In July 1903, 3 workers on a section gang in Ohio were struck by a train that came around a curve without warning. All 3 were killed. The investigation revealed that the lookout had walked away from his position to help with tie replacement, leaving no one watching for trains. The railroad company fired the foreman, but provided no compensation to the families of the dead workers. One documented maintenance worker was Giuseppe Moretti, an Italian immigrant who worked on a section gang in Pennsylvania from 1895 to 1910. Moretti's letters to his family in Italy, preserved by his descendants, describe the work and the conditions. From June 1897. We replace perhaps 20 ties per day when the work is heavy. Each tie weighs as much as a grown man. We must remove the old tie, which is often rotted and stuck in the ballast. Then we must position the new tie exactly where the old one was. The work is never finished. As soon as we complete one section, we start again at the beginning. The tracks must be maintained constantly. Moretti's letters also describe the danger of working on active track. From August 1899, we work between trains. The schedule tells us when trains will pass, but sometimes they are early or late, until we must watch constantly. Yesterday, a train came while we were replacing ties. We heard the whistle and ran from the track. One man, Roberto, was not fast enough. The train struck him. He was killed instantly. We finished the day's work and buried him that evening. His family in Italy will never know what happened to him. The sheer scale of the tie replacement operation is difficult to comprehend. A major railroad in the early 1900s might operate 5,000 miles of track. If each tie lasted an average of 20 years and there were 14,000 ties per mile, the railroad would need to replace about 3.5 million ties annually just to maintain the existing system. That's over 9,000 ties per day, every day, year after year. The economics of ties shape the timber industry. Entire forests were designated for tie production. In Missouri, the Ozark forests were heavily logged for oak ties. In Georgia and the Carolinas, the pine forests supplied southern railroads. In the Pacific Northwest, Douglas fir ties went to western railroads. The tie cutters moved through these forests methodically, taking suitable trees, leaving those that were too small or of wrong species. The environmental impact was significant but localized. A forest logged for ties would be stripped of suitable trees, but smaller trees and non-railroad species would remain. The forest would regenerate, and in 20 to 30 years, it could be logged for ties again. This cycle of cutting and regrowth was sustainable in the sense that the resource wasn't depleted entirely, but it did fundamentally alter the composition of forests in regions where tie cutting was intensive. The decline of wooden ties came gradually with the development of concrete ties in the mid-20th century. Concrete ties don't rot, don't require chemical treatment, and last indefinitely. But they're expensive to manufacture and heavy to transport. The transition was slow. Even today, wooden ties remain common on many railroad lines, especially secondary tracks and industrial spurs. Modern wooden ties are still cut to similar dimensions as the 19th century ties, though the cutting is now done with power saws and automated equipment rather than by hand. Walking across a railroad track today, you're likely walking over a mix of wooden and concrete ties. The wooden ones are the descendants of those 14,000 hand-cut logs per mile. They're made differently now, power tools instead of hand axes, pressure treatment in industrial plants instead of rough creosote application. But the function is the same, the dimensions are similar, and the underlying principle hasn't changed. Rails need support. Ties provide it. 14,000 of them per mile, hidden underneath the steel, invisible to anyone who doesn't know to look. The workers who cut those ties, the Jacob Whitmores in the forest camps, the Giuseppe Morettis on the section gangs, the thousands of unnamed men who shaped logs and drove spikes and replaced rotten ties in rain and snow and blazing heat, they built infrastructure that's still in use. They did it for minimal pay under dangerous conditions. Many died doing it. Most are completely forgotten. There's something profound about hidden infrastructure. We use it constantly without thinking about it. We walk across railroad tracks, we ride trains, we receive goods shipped by rail, and we never consider the foundation that makes it all possible. 14,000 pieces of wood per mile. Hand-cut, hand-shaped, hand-laid, replaced constantly, maintained endlessly, essential to the entire system. The railroad tie is perhaps the most numerous manufactured wooden product in American history. Billions of ties were cut over the 150-year period of railroad construction and operation. Each one required human labor, cutting, shaping, treating, transporting, installing. Each one represented trees cut from American forests, workers in camps and plants, and track gangs. We are a system of production and distribution that operated on a continental scale. And it's hidden. You can stand on a railroad track, look down at the ties, and see them clearly. But you're not really seeing them. You're seeing a few ties in your immediate vicinity. You're not seeing the 14,000 per mile extending in both directions. You're not seeing the forests that were logged to produce them. You're not seeing the camps where workers shaped them. You're not seeing the treatment plants where they were infused with creosote. You're not seeing the section gangs who maintain them. The scale is too large, the system too complex, the infrastructure too ordinary to really register. That's the revelation. That's what makes railroad ties remarkable. Not that they exist, wooden ties are simple, obvious things. But that there are so many of them, that they were all made by hand, that they're maintained constantly, and that almost nobody notices or thinks about it. The infrastructure is invisible because it's everywhere. Think about the last time you crossed railroad tracks. Did you count the ties? Did you wonder where they came from? Did you think about the forests they were cut from, the workers who shaped them, the system that produced and distributed and installed them? Probably not. They're just there, part of the landscape, background, invisible. But now you know. 14,000 ties per mile, hand-cut logs underneath every railroad in America, a forest hidden under the steel, and the next time you cross a track, you might look down differently. You might see not just the ties in front of you, but the scale of what you're standing on. Miles of track extending in every direction, millions of ties, billions of board feet of timber, an entire industry that operated for over a century, largely invisible, to create and maintain the foundation of the railroad system. The workers who made this possible deserve recognition. They weren't engineers or railroad barons or famous builders. They were laborers, tie hackers in forest camps, plant workers breathing creosote fumes, section gang members replacing ties in the rain. They worked for minimal pay under dangerous conditions. They died in accidents that went mostly unrecorded. They're buried in unmarked graves or forgotten entirely, but their work remains. Every time a train crosses the country, it's riding on infrastructure they created. Every time you cross railroad tracks, you're walking over their work. I'm 14,000 hand-cut logs per mile, hidden under the steel, invisible but essential. That's the legacy of the tie workers. They built something so ubiquitous it became invisible. And that's maybe the highest form of infrastructure, so functional, so reliable, so ordinary that nobody thinks about it. The next time you see railroad tracks, stop for a moment. Look at the ties. Really look at them. Think about how many there are. Think about the workers who cut them from forests, shaped them with axes, treated them with chemicals, laid them precisely spaced, maintained them through decades of use. Think about the scale of the system. 14,000 per mile, thousands of miles of track, millions of ties constantly being replaced and maintained. Think about the fact that all of this is happening constantly, right now, and has been happening for over 150 years. And think about the fact that until you read this, you probably never thought about railroad ties at all. That's how good hidden infrastructure is. It works so well that it's invisible. It's there every day, supporting everything that moves by rail, and almost nobody notices. 14,000 hand-cut logs per mile, hidden under the steel. Invisible but absolutely essential. That's the story of America's railroad ties.